host. All right. So at its core, recursion is just a function that calls itself.
Are you trying to share your screen? Because you're not sharing your screen.
Listen, it's early, okay? Recursion is just a function that calls itself. An example, so one of the things that recursion ends up being used for a lot is as essentially a loop where we don't necessarily know how many times we need to iterate or the logic for figuring out how to increment or iterate or something like that. When the logic for that gets really hairy, recursion becomes really useful. So an example, if I had def print 1 to 255, and I had a number, and so a recursive function is broken up into a couple of different parts. One of the most important part, arguably the most important part, is the break case, right? We need to know when to break the recursive call, otherwise you get a call stack size exceeded error, which means that the call stack, which is how many different functions can be called at any given time, there are too many functions being called in there, because as it goes through this function, there's going to be a part where it says print 1 to 255 num. And so if I call this function, and then it calls this function, and then it calls the function, calls the function, calls the function, calls the function, right? In fact, let me just prove it to you. Print 1 to 255, 10. Maximum recursion depth exceeded. So that means that the function called itself, which calls itself, which calls itself, which calls itself, which calls itself, happened so many times that my computer said, I can't call another function. What are you doing to me? I can't handle this. So we need to have a break case. And actually, in this case, we don't want anything. Actually, no. So let's say num equals 1. So if we're trying to print 1 to 255, actually, we're going to start at 255. And I will explain the logic for that in 1 second. Generally, what you want to do is start at the top and work your way down, because what eventually happens is it works its way down, it whittles down till it reaches a break point, and then it shoots back up the call stack. So if I say if num equals 1, print 1, and then print num, or print 1 to 255 num plus num minus equals 1. Num minus 1. No, num minus equals 1. Sorry, I'm all over the place right now. Okay, so if I run this now, 1 to 255, 1. Oh no. Maximum recursion depth exceeded in comparison. 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. Why is it doing that?
Cody, I think because your exit condition is if it is less than or equal to 1, just print 1. That's the only thing, right?
Yeah, but...
So at that point, num will be 1.
There we go. Okay. All right. I don't think the return was necessary. Let me clear this output. Oh, it was necessary. Okay.
So why is the return necessary?
So I know in oh no, never mind. I'm a big dumb. It is required because if it doesn't return, then it breaks out of the if statement and goes into there. I could have negated the need for that return statement by putting this as an else. If I don't have the else, I need to have the return because it'll say if num is less than or equal to 1, and I can put this back to equal to 1, then print 1, then return. If I didn't have this, if num is 1, it'll print 1 and then go down here. Otherwise, if I do return, so basically what's going to happen, let's do 1 to num, and I'll just say num is here and just make it 3, just to make it a little easier. 1 to num, print 1 to num. Okay, so if I call print 1 to num, num equals 3, and then the next step is call or check if num is 1. It is not. So we go on to the next step, which calls print 1 to num with num minus 1, which is print 1 to num of 2, right? So then, wait a second, I can draw things. All right, so if I T-diagram this, right? My first function call, num is 3, right? Is num equal 1? No. So then it goes down to here and calls the function again with num minus 1. So in this function call, num is 2, right? Is num equal to 1? No. So then it goes here again and calls print 1 to num. So we say num is 1 because it does num minus 1, puts that in here, right? So is num equal to 1? Yes. So then it prints 1, and then there's this implicit return statement right here, right? So it prints 1 and then returns, and when it returns, it's back here, right? Because this is where the function was called. So then what's the next line after this?
Why is there implicit return?
That's just how Python works.
Is it
If it reaches the end of a function and there's no return statement, then by default, Python will return and terminate the function.
Okay.
So after this function call ends, and it prints 1 because num equals 1, and then it hits return, where do we return into? Where was the last place that this function was called? Here, right? And what's the line of code after this?
Print num.
Right, print num. And when we go up here into this function call, what is num?
2, but
right, it's 2. So it prints num, and then it hits this implicit return statement and returns up to this function call, right? So if I run this, I get 1, 2, 3. If I change this to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Because essentially what it's doing is on the first function call here, num is 10, right? Is num equal to 1?
No, it's not.
No, it is not. So then what do? We call the function again, right? So this is call number 1, right? And then from in here, we call the function again. And this is call 2. But we called it with num minus 1. So what is num in here?
9.
9, right? And then so is num equal to 1 in call number 2?
No.
No. So then we go here again and we call print to num again. Call 3 num. What is num now in
8.
this function call? 8, right? Is num 1?
No.
No. So then we go down and we call again. Call 4. What is num in the 4th call?
7.
7, right? Is num equal to 1?
9.
No. So we call again. What is num in this function call?
6.
6. Is the num equal to 1? No. So we call the function again. What is num in here?
5.
5, right? Is num equal to 1? No. So we call the function again. This is call number 7. What is num in here? 4. Is num equal to 1?
No.
No. So we call the function again. Call 8. What is num in here?
3.
3. Is num equal to 1?
Nope.
Nope. So we call the function again. And what is num in here?
2.
2. Is num equal to 1?
Mm,
No. So we call the function again. And what is num in here?
1.
1, right? Cool. Is num equal to 1?
Yes.
Yes.
Cool. So then what do?
Print.
Print num.
So we print. Awesome. And then what do we do after we print 1?
Print everything else.
Well, but in this function call, in function call number 10, right?
Hmm.
We determined that this is true, and then we did this, so what do?
Return.
We return, right. So then in that case, this function call is over. It has already
So-
printed 1, and we're
After-
back in call number 9.
Oh.
And back in call number 9, we just finished running this line of code. So what do we do next?
You print num, right?
Right.
Num, which is 2.
Oh.
right.
Jesus, Thomas.
So
And
just-
then down here at the end, we have this implicit return.
Okay.
So after it prints 2, what happens?
It calls the function again, or no?
It doesn't call the function again, but it returns, so it
Right.
it terminates that call, and we're back in here. So what happens after this line? Because we're still waiting on this line in each and every single one of these call stacks. All waiting on line 9, right? Every single one of these is waiting on call on line number 9 for that line of code to terminate, to return from this function, right? So every single time that the function that it called, right, call number 1, 2, 3, 4, 5, 6, 7, 8, 9, if call 8 finishes by printing the number, then it pops up to call 7, where it is waiting on that same line to finish. And it finishes and it prints num. So as you shoot your way back up this call stack, you're printing 4, 5, 6, 7, 8, 9, 10. And then you return from the very last one, and you have completed a recursive function.
So what is some functionality besides counting numbers that like recursion would be useful for?
So one of the most easy to use cases for recursion is you'll get to something called a binary search tree. Now, I don't know if you guys remember, last week we did binary search, right? And it was this whole, we either look on the left side or the right side of an array, right? And then we whittle down the range of indices that we're looking at to find a certain value, right? You guys remember that?
Yes.
At least somewhat? Right, cool.
Yes.
Yes.
So there's another data structure called a binary search tree. Where rather than being just an array of numbers, it's actually similar to a singly linked list in that it is a tree of nodes. So you have a node that has a value, a left, and a right. And each left and right points to another node, which has a value, a left, and a right.
Wait, what
Now-
do those little things represent inside?
Value,
Oh,
left, right,
okay.
We're
right?
just calling it this so that you get away from the dingly linked list.
No, this is, so a dingly linked list looks like this. And it's called a doubly linked list. But a doubly linked list would look like this. You have a head, which has a previous and a next. And that node, and a next. And that node has a previous and a next. And that node has a previous and a next. And that node has a previous and a next. Right? That would be a dingly linked list.
A
Doubly linked
singly
list.
linked?
Doubly
Wait.
linked list.
What's the difference between a double and a single? Like,
A singly linked list only has a value. Each node individually only has a value and a next. In a
Oh.
doubly linked list, each node has a
oh, they
dot
have a
next
previous.
and a dot previous.
Okay.
Wouldn't a doubly linked list be easier to work with then? Because you have a
Yes,
previous-
but it essentially it doesn't double, but it increases your storage like needed
like your
by
data?
50%. Yeah, because you
Okay.
have to keep track of 2 things per node. So anyway, so you have this binary search tree, right? And the way that it generally works is if this is 10, everything to the right of this node is going to be greater than 10. Everything to the left is going to be less than 10. So this would be like 7. Everything to the right of 7 is going to be greater than 7, but less than 10. So that would be something like 9. And this might be 6. And then this might have a left of 8. And this would have 12 with a left of 11 and a right of 14 and a left of 13 and a right of 15, right? Now, you could theoretically write a while loop to traverse through this thing, but that's going to be a nightmare. Recursion makes this a lot easier. So that's like the easiest, or well, not the easiest, but the most like logical use, where, because as you progress through this, if you were using a while loop, you would need a bajillion different things to keep track of the previous node and that thing's previous node and that thing's previous node, so you know how to work your way back up to wherever you started. Whereas with recursion, you are naturally keeping track of it with your recursive calls, right? Because once it shoots back up the call stack, it eventually gets back to the initial call which is still waiting at the place that it was first called at. But that's a whole other monster. You will be getting into those relatively soon, sometime within the next few weeks, I think. But today we have 2 algo challenges, or we'll start with one. How many of you know what sigma notation is? So essentially, the function is some num. So the sigma of a number is, if my number is 4, the sigma of, oh god, I forgot the actual syntax. I think it's n equals 4 with 1 at the top or something like that.
Sigma equal to 10.
It looks something like this. So the sigma of 4, or maybe it's 4 with n of 1. I don't remember exactly what it is. Is essentially 4 plus 3 plus 2 plus 1, right? So if num is 5, the sigma is 5 plus 4 plus 3 plus 2 plus 1. Now you could use a while loop, while num is greater than 0, sum plus equals num minus equals 1.
What is this? Oh, not that one. The other way. I messed that up.
What?
What is that number?
So I don't remember the specific syntax. Let me pull this up. Sigma notation. Okay,
Sigma
so
and in the bracket number.
yeah, okay, so it's the actual notation looks something like this. So you have a sigma, you have n equals 1, 4, so this should be num. Go to this value. What?
No, Cody, sigma and this num in the bracket, sigma of number equal to, it automatically adds the numbers, whatever the number be.
Okay, so it's just
sigma
this,
of
right?
number.
Okay,
Yes,
yeah.
sir, yep.
So starting at 1 to this number, what is the sum of every number in between? So it's essentially 1 plus 2 plus 3 plus 4 plus ... plus num, right? What is the sum of every number between 1, every integer between 1 and that number? So the challenge to you today is to write a function using recursion. Write a sigma function using recursion where sigma of 4 will return 4 plus 3 plus 2 plus 1 equals 7, 8, 9, 10. Yes, Tash.
Why are we doing this instead of just studying for the test?
Excellent question.
Because algos are still very important, and overall, I think the majority of you did pass your belt exam. And you could take an hour out of your day for algos. You have
Okay.
23 other hours each day.
Can we take the belt exam today?
No, not today. It's too much to keep track of if it's just like 1 or 2 people on top of all the other stuff. So I'm gonna have everybody hold off until tomorrow. If you're ready for the belt exam today, then take today to start working on your projects, and just be ready to go tomorrow.
Okay.
Cool. All right. So any other questions on this function before I get you guys kicked off?
Could you explain sigma a little more?
Yeah.
Sorry, I didn't understand.
Okay. So in math, there is a thing called sigma where you have n equals 1. This is the number to start at. And then you go to some number, right? If this is 4, sigma of 4 is 4 plus 3 plus 2 plus 1, which equals 10. So sigma of 4 equals 10, right? So write an algorithm that if I give you the number, you can give me that number's sigma, which is the sum of all integers between 1 and that number.
Oh, well, how did the n equals 1 relate to that?
That's where you start. It's just the way that the mathematical formula works.
Oh, it's just saying you start at 1. Okay.
Yeah, because you can specify what number you want to start at, but assume that it starts at 1. Sigma 4 would be 10. Sigma 5 would be 15. Sigma
Okay.
6 would be 21, right? So write an algorithm that given it's a sigma function using recursion where sigma 4 will return 4 plus 3 plus 2 plus 1. Will return the
Should it return 10 or 4 plus 3 plus 2 plus 1, the complete? Should it return just the sum of just the sigma, or should it return the complete equation?
no, just return the actual sum of all the numbers.
Okay.
Any other questions? All right. I will copy and paste this code into the Zoom chat, and I will get you guys all split up. Dennis and Kamakani, are you guys all working together today, or?
No, I'm out of that group today.
Okay, then it's all random for everybody.
Shit, I should have said yes.
Ready, break.
So I'm wondering how we can pass the
I think we can do it.
value.
I
Sorry?
think we can do something. I've sent it in chat.
I don't know where my chat box went.
I had a hard time finding mine too.
So you want to be using the output of the recursive line somewhere, right? Probably in the sum equals plus plus something, right? Because you want to be adding the result of the function to your sum. Is Cody in here? Oh no, Cody, stop.
So bad.
So we want to use this here to actually be. So when we call on this, right now it's not actually saving the information, right? Is what you're saying?
Yeah.
Yeah.
So you probably want to declare it to a variable or something, so you can use.
Cody's here.
There's
Come on,
Cody.
guys.
Should I share?
Yeah, we did it.
There you go. I can't hear you.
Yeah, same
Are you
stuff.
talking?
Whoops. Yeah.
Oh, there
sorry.
you go.
Good work. So in that case,
No. Factorial. Oh shit. Ah.
Oh, okay.
do that.
We
No.
can just change this.
Updated sample.
Oh, 0 is in there.
Factorial. No.
You guys are too smart for me.
Did it work?
Yeah.
Okay.
Well, you guys are good then.
Yep. It worked. Awesome.
Hi, Cody.
Hello.
I see you.
Yes. That's how this works.
Yeah, no idea. No idea.
It's hitting that return down there. That's why.
Yeah.
Because once it passes the if statement, it hits the return, then goes straight back up. So you might have to take out the returns in order for it to actually hit down there.
Yeah, that is what. Where does this go? That is what we're trying to do.
Comes from up here. Well, it comes from your previous from up above it, right?
It should come, Cody. So what we were trying to do is we were trying to do this so that we were thinking that it will come from here.
Exits. Exists. Only within the.
Within this function, okay.
Okay.
This exists only within this function. So sigma of num. We tried that before. This is what we tried. Oh.
See, I knew it. I knew it was the return statements. What because it returns the if statement. What comes out of that if statement comes back up. Return returns.
Nothing. Five returns. So do we take out the returns?
Return num.
You don't want to take out the return. So if you are saying y equals print one to num, right?
So this is the num. Okay, so this becomes whatever the num is here.
Mm-hmm.
So it saves the num here, and then y becomes the num that is saved here. This num. So this also has to be num.
Yes, but now the problem is none of this here is recursive, right?
Yeah. So the num keeps changing.
But this
so
is not. You want this. This function should be recursive.
Oh. Okay, so we need to make this function recursive and then call that.
This just as an example.
Okay, got it.
Okay, we were actually trying to use it.
Yeah, no. You don't want to integrate it. You don't want to like incorporate that into your algorithm. You just use that as an example of what a recursive function looks like.
So the example that we thought we should use that function.
Yeah, no, you don't want to do that.
So we wanted to call it.
Nope.
Okay.
All right, cool.
Okay. So
Hey Cody, we're finished.
Yeah, what'd you get?
Jancy should take all the credit.
No. So I'm returning num over here, and I'm receiving it in some temporary variable and then adding it to the
Oh,
num
wait.
that we have.
Cool.
Did we use recursion?
Yep.
Oh.
Yep. It's recursion because the function is called sigma, and within the sigma function, you are calling the sigma function. So when you do this, it goes back up to here and starts running this way. So then when it hits this line, it goes back and calls it again. And it'll keep calling it until something says, no more.
Yeah,
And
I don't
that's-
need this sum variable. I think we should remove it. There was no use of it. I did nothing with it. I had planned to. Should work. Oh, I called it with. Did it do something? I don't know. I can't look. Oh, I've been doing the wrong one.
So since our method name is sigma itself like a built-in function in Python coding?
Nope.
Oh,
Nope.
just the name of the function.
Sigma is a mathematical concept.
Yeah, it's just a regular variable name, isn't it?
This can be slipper as long as you replace it anywhere.
Then how does it know it's using the sigma math in the method?
Because you're creating it. This is doing that, right? So if you call sigma with num of 3, right? Is num equal to 1?
No.
No. So then what do?
It goes down until it hits 1.
So yeah, so we say temp equals what? We don't know.
Which is the num minus 1, which is 3 minus 1, which is
But
2.
it's not num minus 1. It's the function call, right? Temp is equal
Oh.
to sigma. So this
Oh.
is sigma of some num, right? Think of it that way. So num is 3. So we call the function, and num is 3. Temp is equal to whatever comes back from another function call. So in here, what is num? Because
2.
when we call this, it's num minus 1, and num was 3 in here when we call this function.
Oh.
So now num is 2 inside of this function. 2
Okay.
is not equal to 1, so we say temp equals another sigma call, right? And we still don't know what this temp is because we're still waiting on this sigma call to terminate and return. And so now we have num is 1, right? Is num equal to 1?
Yeah.
Yeah, it is. So then what are we going to do? We're going to return num. So in that case, temp is 1 in that function call, and this function call is over. So what is this going to return? 2 plus 1, right? Because it returns temp plus num. Oopsies. So this
Okay.
returns 2 plus 1, which gets returned up here. This is 3 plus 3, because temp is 3. Well, I guess I should say. Return 2 plus 1 up there. So temp is 3. And then all of this goes away. And then what do we return? 3 plus 3, which is 6. And that gets returned. So if you ran sigma 3, you should get 6.
Why?
What do you mean why? I just did the whole logic. I just walked
Sigma
through the whole
3.
thing.
Why is 3 6? I get everything but that part.
Okay, let's do this again.
2 plus 1.
No.
What do you you want to know why, but you don't want me to explain it again. So
I don't know. Everyone else has to watch it again too.
sigma of 3, right? So what is num?
3.
3, right? And so is num equal to 1?
No.
No. So then what do? We say temp equals sigma
Okay, I get it now.
is sigma of 2, right?
Okay.
So if we call sigma of 2 again, what is num?
1.
No,
What?
2.
num is 2, right? If
Oh.
sigma of 3 inside of
I
that
see.
function num is 3.
I see.
So now temp is equal to whatever this is going to return.
Oh.
And how do we know what it returns? Well, we have to run the function. So we run the function and num equals 2. Is num equal to 1?
Yeah.
2 is equal to 1?
What? Oh, I thought we decremented in the next T, right? I guess we don't have the next T.
Well, we haven't yet.
diagram.
That we haven't gotten there yet, right? So inside of the 3, we decrement num when we call sigma of num again, right?
Okay.
So when we do that, temp equals sigma of num minus 1, which is 2, right? Because 3 minus 1 is 2.
Okay.
So then when we call sigma of 2, we call this whole function again with num of 2. So num equals 2 in here. And then is num equal to 1?
Oh. No.
No. So then what do? We say temp equals sigma of 1 because we do num minus 1. So then we're calling the function again. So in this function, what is num?
1.
Right. So num is 1.
Num is 1, return num.
Well, yeah, so we don't even do the temp thing, right? Because if num is 1, return num. So
Oh,
if num gets returned up here, sigma of 1 gets replaced with 1,
oh,
right?
okay. Oh, I see. It's the sigma in the T diagram.
Mm-hmm. So this is 1, right?
Oh,
And then what do? We return two plus 1,
where do
right?
we? Oh, temp plus num?
Yeah, and temp is 1, num is 2. So we return 2 plus 1. And what is 2 plus 1?
3. But
Right.
when we have temp equals sigma minus num minus 1,
Mhm.
are we not subtracting again when we go back up?
No, because that line of code has already run. And
Oh,
we're just waiting on sigma of whatever num minus 1 is to get back.
we're just hitting all the temp plus num.
Yeah, and we're not actually
returns?
changing the value of num. We're just saying whatever number minus 1 is, send that number through. But num is still equal to what it was originally when this
Oh.
function started.
Oh.
So
Right,
then,
that's why we just had 1 each time.
yeah, so then this doesn't return just 2 plus 1, it returns 3. So that comes up here. And then we replace sigma 2 with 3, right? And now this function call is done. So what do we return here?
3
3
plus 1.
plus 1? Is that what temp is?
3 plus 3.
Right? Temp is 3.
It is.
Mm-hmm.
Oh.
So we return 3 plus 3, which equals 6. So sigma 3 equals 6.
Oh. When did temp become 3? Is that what we just did? But num
Mhm.
was supposed to stay at 1, wasn't it?
In the previous call stacks.
Oh. Oh, did we get, since we're back at the top original T
Num is
diagram?
still 3 inside of that function call.
Oh, we got to the top of it where the original number was
Mhm.
passed.
Right.
And when we originally passed it, it was 3.
Right.
So then we adding the temporary one that was incremented.
Correct.
To num. Okay.
All right. Cool. All right, I'm going to pull everybody back.
Do it. Hello.
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 Hola.
Hola. Yes, Thomas.
May I help you?
You just whispered my name.
He just likes being a creeper.
He really does. He does it well.
Why didn't Tori show up today?
Tori's internet is broke.
Oh no. That's no
Oh,
bueno.
Yeah.
Oh no, the coronavirus got to his router too.
No,
Oh, God.
he's been in the process of upgrading to fiber. So there's been issues
Oh,
with.
sweet.
He
I'm
doesn't
on
deserve pity if he's getting fiber.
Why
Thomas,
not?
you're just a terrible person sometimes.
That is also very true.
What do you mean sometimes?
All right. I think everybody's back in here now. Who wants to present?
Did anybody get it working?
Mm-hmm.
Oh, well. That wasn't me, obviously. We couldn't get it working.
Neither
Okay.
could we.
His life beats better.
My team couldn't get it working, but one person on our team got it working by themselves.
So
Wait.
who wants to present?
Michael, do you want to do it since it's on your computer and it's working?
Dennis said, hey. Song can do it.
I vote for Fez.
I hopped into like 3 different rooms that had it. Why is nobody's volunteering? What's going on?
Oh, I don't.
Thomas can do it. All right, Thomas. Thomas. Frumpy
So
cat.
you can't just like volunteer other people constantly.
Yeah, but Thomas did it. And I know Thomas knows how to do it. And Thomas hasn't really presented in a while, so.
Hey, that's not nice.
Why is it not nice? Why is it not nice?
Alright, fine then.
Yeah.
How do I
present
share
some
screen
code.
again? Okay. Can you see this?
Yes.
Okay, so it works.
What do you? Okay, walk us through some logic.
Okay, so
Diagram some stuff.
I don't actually know how to T-diagram recursive stuff.
What?
So,
All right, so pick a smaller number than 30.
all right.
Okay, come on, Thomas.
Okay. So
All right.
basically, it runs recursively until it hits the exit condition, which is if num equals 1. So if it does that, sum will be returned to 1, and then it'll keep returning sum to this statement. And then sum equals the sum from all the previous iterations plus the num it's currently on. So when it's on 2, it'll run 1 plus 2, and then it'll return 3. And then on the previous iteration, it'll have sum equals 3 plus 3, 6. And then after that, you'll have 6 plus 4. And then it keeps going. Yay.
Okay. Well, I will T-diagram this then. So we call print R of 5, right? So when we call print R5, num equals 5. And sum equals 0, right? This check does not work, right? Num is not equal to 1. Num is not less than 0. So we call this. So which says sum plus equals, so it's 0 plus print R of num minus 1, which is print R of 4, plus num, which is 5, right? So print R of 4, num equals 4, sum equals 0, right? So in that, this check is a no. This check is a no. This check is a yes, right? So then we say 0 plus print r of 3, right? Because it's num minus 1 and num is 4. So print r of 3 plus num, and num is 4. So print r of 3, num is 3, sum is 0. So we run our if checks, right? Num is not 1. Num is not less than or equal to 0. Num is going to fall into this else, right? It's not either of those, so we go into else. So sum plus equals. So sum is 0 plus print r of 2 plus num, which is 3. So print r of 2, num is 2, sum is 0. Run our if checks again, right? Oops. Num is not 1. Num is not less than or equal to 0. So we hop into the else, right? So sum plus equals, so sum is 0 plus print r of num minus 1. Num is 2, so num minus 1 is 1, plus num, which is 2, right? So now let's print r of 1. Num is 1. Let me rewrite that guy. Right? Num is 1. Sum is 0. So we run our if checks. Is num 1? Yes. So then we say, is that sum minus 1 or sum equals 1?
Equals 1.
Okay. So then sum is now 1. Right? And then we return sum. So when this gets returned, we replace print r of 1 with what gets returned. And 1 is returned. So what is sum? Sum is 0 plus 1 plus 2, which is 3. Right? And so in this call, we are on this line. And when we finish that line, what do? Return the sum. So this gets returned up to here and replaces print r of 2 with 3. 0 plus 3 plus 3 is 6. And then we return. And this gets returned up here and replaces this with 6. 6 plus 4 is 10. This gets returned up here where it was last called and replaces that function call with what's returned, which is 10. 10 plus 5 equals 15, which gets returned. And print r of 5 gets replaced with 15. And that's why print r of 5 equals 15.
Yeah.
Do it again.
Do it again?
Just kidding.
I can do it again. Replace r with replace num with 3, Thomas, just so that I can go through it again. And I saved the screenshot so I can send that out to you guys.
Not 3.
Okay. So print r. No, we're going to do 3. Cool. So sum is 0. Or no, I'm going to do it the way that I did it a second ago. Start with num is 3, right? Sum is 0. Let's do our if
Okay.
checks. Is num equal to 1? No. Is num less than or equal to 0? No. So we pop into our else. Sum plus equals, so 0 plus print r num minus 1. What is num minus 1?
2.
Cool. Plus num, which is
3.
3, right.
5.
Well, 2 plus 3 is 5, yes. But we don't want 2 plus 3. We want print whatever this function returns.
Okay.
So we call the function, and when we in this function call, num is 2, sum is 0. So we run our checks. Is num
Oh.
equal to 1?
No.
Is num less than or equal to 0?
No.
No. So then we pop into that else statement again. So sum plus equals, so sum is 0 plus print r of num minus 1. And what's num minus 1?
1.
Right. So 1 plus num, which is 2.
Okay. Wait, when did num become 2?
In the previous call, initially num was 3. And then we ran print r of num minus 1. So what is 3 minus 1? 2. So we called print r of 2. So this is call number 1, call number 2, call number 3. So in call number 3, num is 1, sum is 0. So let's run our if checks again. Oops.
Is sum
num is
not
the
equal to
value
1?
that we.
When num is equal to sum, if num equals 1, sum is equal to 1, right?
Yes. So num equals 1, which means that sum equals 1.
When num equals 1, why did you write 0 here?
What?
In the T diagram.
Because when we first jump in, before we run any if checks, sum is equal to 0.
Okay. Okay. Yeah. Sorry.
And then I find out that num equals 1, and now I replace sum
with
instead of being 0 is 1.
Okay.
And then I return sum. Which means that 1 gets returned up here and replaces this function call with that number. And then back in call number 2, call 3 is done. In call number 2, we're waiting on line 11 for this function to finish. It's just finished, and we've replaced it with 1. So sum equals 3. Because 0 plus 1 plus 2 is 3. And then we return sum, which is 3. So this gets returned up here. This is 3. Sum is 3 plus 3, which is 6. So we return 6, which gets returned up here. So print r of 3 equals 6. Cool. Questions on recursion?
Can we do one more problem with recursion? Just to get our heads.
Yes, but I will make this just like optional because we do need to hop into some other stuff. But let me.
Oops.
Factorial. Does anybody know what a factorial is?
It's a place where they build stuff.
That's a factory.
Factorial.
So factorial is a really excited number. It's 4.
You say it really loudly.
Yeah, but it's not actually that, right? 4 factorial is 4 times 3 times 2 times 1. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. So practice recursion by
#1 educational Twitch channel right here.
write a factorial function using recursion, where factorial num will return the that number. Example. All right. So that is another good practice. We will be doing another recursive algorithm tomorrow, or not tomorrow because a lot of you guys are retaking. So Thursday we will do another recursive function. I will, let's see, git add all, git commit. Oh wait, actually, hold on. Let me come in here and just get this one. If num equals 1, num plus equals sigma 1. Let me just check. Cool. Yeah. All right. Algorithm for returning for recursively solving sigma or summation e sigma 4 equals 4 plus 3 plus 2 plus 1, which is 7. No, 10. All right. Let me get this up on GitHub for you guys. All right, the same GitHub where I have been putting all of the algos is now updated. So you have some code here and you can test out factorial stuff. All right, so take about 15 minutes or so. If you have finished your belt exam, I will be doing an AJAX lecture. So for those working on your projects and interested in some of the functionalities of AJAX, hop back into this Zoom call If you are prepping for your belt exam, I don't want to distract you, so either just mute the Zoom call or, just hop out of it. Yes, Tash.
Dakota gonna be around today?
Yes, of course he will. But he
Oh,
will be
cool.
here at about 1 o'clock, I think. So he will be running that afternoon breakout session for those still working on belt prep stuff. So keep an ear out on that. He will announce his arrival on Mattermost, and he'll pop in and say hello, and then we'll get everything situated from there. But in the meantime, I will be doing the Ajax demo. So hop back in here. Actually, push it to 11 o'clock. We'll do that. So 11 o'clock in here, Ajax. Cool? Yeah, no.
Cool.
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 Yay.